Good morning, folks. This is lecture 2 of week number 4, and today we're going to start the subject of analyzing assemblies. I do want to point out to you that if you don't remember some of the stuff and maybe you forgot it completely, I strongly suggest you go and review some of the things that you did in the advanced engineering and design course that you did in your second year using CATIA. And there you have done assemblies, of course. Now, the kind of information that we need here is fairly basic, so it doesn't deal with advanced material. Therefore, it should be easy for you to refresh your memory by either going to YouTube, watching some videos, or going to your lecture notes from that course. Now, here is the agenda for today. I'm going to analyze a tensile specimen, which is modeled as an assembly. And in doing so, I'll do it several different ways. And one is without any planes of symmetry, and then with all applicable planes of symmetry. If you go to this problem, you have a block of this dimension, and we have two pins which are inserted into those holes, and these are symmetrically inserted. So overall, you have a geometry like that. Now remember, when you look at this part on the right side, you should not get the impression that this is an object that was casted like that or machined like this. It is a block with two holes, and you maybe bought or made two pins and you inserted it into those holes, which means that there is contact between the surface of these pins and the surface of those holes. Okay. Now, the bottom end, the bottom end faces of this, the end faces of this bottom pin are clamped, and the two top faces of the pin on either side is being pulled up by the amount 100th of an inch. What we like to know is what is the force needed to create that deformation, and also what are the stresses in the part. Now, as it is stated now, in other words, the bottom pins are clamped and the top are pushed up. If you look at this geometry, you'll notice that there is one plane of symmetry, which is XZ, and another plane of symmetry that is YZ. Okay? XY is not a plane of symmetry. In other words, if you cut this thing in the middle, the top and the bottom do not look the same as far as the restraint and load is concerned, and as far as the stress distribution is concerned. However, if the top pin was pulled by 0.01 upward, and the bottom pin, instead of being fixed to the two ends, was also pulled down by the same amount, then XY would be a plane of symmetry. But present problem, there's only two planes of symmetry, XZ and YZ. So I'm going to do this problem two different ways. One is without any planes of symmetry, okay, which is not the way it's supposed to be done if this is given on a test and you're specifically asked to use use all applicable planes of symmetry. But I will do that anyways without any planes of symmetry. And then I come back and cut it two ways, XZ and YZ, and we're going to analyze the same problem. Okay, so let's go ahead here. Notice that I'm starting with a product file in the past up until today. I always close this and started a part file. But because this is an assembly, we're going to need a product. We're going to insert all the parts in it, make them one by one, and then save the whole product, and automatically all the parts in it. And when we go to the generative structure analysis, a file is going to be created, CAT analysis file. So when it comes to submission, you have to give us the product file, all the part files that are in that product, and the CAT analysis file, which has the finite element approximation in it. Okay, let's start making the block actually. So we're going to say insert a new part in there. And I'm going to call this thing a block. Right click, properties, block. This is the instance name, and you go down below it, and there is your part name, block. Category does not have part name, it has part number, you know that already. And you want to make that block, so double click on the block, and on that vertical plane, I will sketch that cross section that you have, because eventually I'm going to be doing some cutting. I'm going to make this thing a symmetric rectangle, and let's put some dimensions here. Remember, first time we're going to do it without any planes of symmetry, so this thing is 10 inches. And this bottom piece is, I believe, 4. Okay. And then we have 2 little holes here, so one of them is going to be like that. The dimensions are given from the center to the top. The dimension from here to here is 1 inch, I believe. Let me move this thing up. So this is 1. And the diameter of this thing is also 1. So radius is 0.5. Good. Now, instead of making this thing exactly down below it, I can always mirror this. So you click on the mirror. Just read this thing at the bottom left corner of your screen. Select the thing that you want to duplicate. So this is the one. And select the axis with respect to which you want to mirror it with respect to this. Okay. Exit. And then symmetrically, we're going to pad it. So 0.5 in each direction. That gives a total thickness of, mirror extent, don't forget. Total thickness of 1 inch. That is exactly what we have in this geometry. Now, then I'm going to say insert top pin, insert new part. This says, do you want to use a new coordinate system, or do you want to use the assembly coordinate system 0, 0 as the coordinate system for origin for the part? So I always say no, because I always want this, whatever I do is to be aligned with the global assembly coordinate system 0, 0, 0. I'm going to rename this thing to be properties. This is going to be top pin. This is the instance name. You scroll down here. And this is the part name, top pin. Okay, let's make it. So double click on the top pin. Now I have to draw a pin of this diameter. If that is the case, why don't I go on the XY plane, XZ plane, and sketch in it, project that circle, where there's a project that circle. So instead of me drawing a circle that size, I'm going to project that circle, and then when I exit, I can actually pad it, mirror extent, 1.5 inches in each direction. So there we are. Now, I have to repeat the same thing for the bottom one. It is crazy because I can copy and paste this, or I can actually literally insert a new part in it and make it. Or if I save this thing, if I save this assembly, then I can insert an instance of this part, top pin, because they look identical. And the reason I say that, when you copy and paste 100 bolts, for example, that takes time. That takes time and it takes space. But if you do one bolt, in this case one pin, and insert an instance of that pin or instance of one of those 100 bolts, then it's a lot more efficient to do this problem. Okay, but I will insert the ugly way, new part, no, I'll call it bottom pin. We don't care how you do it on the test, as long as you do it right. Bottom pin. Scroll down. That was the instance name. This is the part name. Bottom pin. Let's make it. double click on this. We do exactly the same thing. On that vertical plane, I use a sketch. Notice that the steps are identical. So we're going to project there. I think it's projected. Did it not? Maybe not. Let me check this. Yeah. I think I inadvertently let me project that circle there. Now it is. Okay. And it's actually this curve that you see here. And exit. And once again, padded, mirror extent, 1.5 in each direction. Now, one thing I want to point out to you is that, well, first of all, let's go all the way on the top. Let's go all the way on the top. That's all the way top level assembly. If I click on the floppy, everything that you have done, okay, let's actually do that. I don't want to do it like this. I want to go to File, Save Management. This is the block product that I want to save as, Desktop, New Folder, Tensile Assembly, or Tensile Specimen Assembly. So we say OK, and say OK. What it does, it takes the product and all the parts in it and puts it in that folder. So if this was a test problem, at the end of the day, when you're done with that particular folder, you have the product in it, you have all the parts, and later on you have to save the analysis, CAT analysis, in that same folder and upload it to where you're supposed to do. Okay, good. Now let's say that everything is made out of steel. If that's the case, I don't have to go and do this part by part. I click on Apply Material. I'm going to use the steel on the product, which automatically puts it on all the parts. You see that? It's down here. It puts it on all the parts, and click on the floppy, and done. Now, in anticipation of me going and doing this thing with a cut in the X and Y Z plane, what I can do, I can split this thing. I can go to assembly design. Right now, you see that? Right now, I am in assembly design, 2 gears. And there's a split here. Remember, there was a split in part design. There was a split in generative shape design. And there is a split here in the assembly. So I can split several things in the assembly at the same time. At some point, when I decide to do this thing with cuts that are present, I have to come back and do that. Or I can do it now and deactivate it. That's entirely up to you how you want to do that. So I will not do that right now. I will wait until I finish this thing without any, run this problem in finite element without any planes of symmetry, and then I come back to the assembly design, split it, and go back and do the rest of the problem. Okay? Good. So I'm not going to split. I can, and then deactivate it as if it was not here. No, we're not going to do that. So let's go to generative structure analysis simulation, generative structure analysis. Oh, let me cancel that. Go back. Notice that right now I created things which are in the right spot because of the way I did it. But if I ever move these things, and I decided to put them back in the same place, it's not going to happen. So let me actually remind you how you put assembly constraints. So let me move these things. There is this toolbar here that says Move Toolbar, and one of them is Manipulate. I like this. Instead of moving things with the compass, for example, I can translate this pin in the Y direction, and this pin in the Z direction, and this pin, I can rotate it about, for example, some axis. Let me do this X. It's easier to see what's going on. It's kind of hard to see it like that. Let me see now about X. Yeah. Okay, good. Sorry, this is translate. Sorry, rotation. Right there. Okay, good. And same thing right there. Okay, good. Notice that if I say okay, then I'm all done. There's no assembly constraints. First thing I'm going to do is I'm going to use the anchor, this anchor, to fix something, and it's going to be this block. And then I'm going to insert, using coincidence, I'm going to put axis of this and axis of that. And if I update, you see that they line up. And coincidence between the vertical plane, this is the vertical plane of that pin, and the block. So that's going to be exit plane of the block right there. And say OK. And update is going to be, oops, maybe I picked the wrong stuff. So let me go back here, delete this, read it again. Let's be careful. So coincidence between the, let me see, between the, let me see how these things are. Okay. Exit plane of this pin and the exit plane of the block, which is this. Yeah, that's better. And update, it's going to jump back there. And coincidence between this axis and that axis, and coincidence between the exit plane of the bottom pin and the exit plane of the block, and update there. Now, if I move these things apart, if I do any crazy stuff to it, like that, and like this, because I have assembly constraints, if I update, they go back to where they belong. Okay, now that we sorted this out, so let's go, first of all, save everything, because these constraints were not saved. As far as we are concerned for problems, we don't care whether you put these assembly constraints or not, but make sure you can finish the problem, the finite element one that we want. So we're going to go to generative structure analysis and simulation. Generative structure analysis. CATIA sees three solid parts, immediately measures each one of them. And you can see actually in the tree, each one of these will belong to something. This one belongs to the block. This is top pin. This is the bottom pin. And say OK. Or you can see it in the screen too. And this is too big. So what I'm going to do is I'm going to make this element of the block, smaller around the hole. So let me hide this. And this one was for the block. What you do is you go here. Remember how you do local refinement right there? We have done this thing many times. Okay, and then this is the one that we want to refine. And it says where. So I wanted to do it right here. So what it does, it actually takes a small element. You see that? Depending on what size you have here. So maybe I should make this thing 0.1. See how it looks like? Yeah. So it's a little bit smaller. We say OK. And by the way, if we say, show me the mesh, right-click mesh visualization, you can see that everything is meshed except that for the block around the hole, this is finer. So deactivate. Let me also do the one at the bottom. So same story. Let me hide this. Actually, what you can do, you can hide this, no problem. When you double click on this, it says where. So I took that face, top face, and I can also select the bottom face. So you can do it at the same time, or you do it separately, whichever you want. Right click mesh visualization. You see that you have finer mesh around the hole in the bottom and the top, both of them. There we are. There is no reason to make a fine mesh in this area because not much action is happening. Remember, you look at the critical area where the stresses are closely packed. Those are where you have to do your refinement. By the way, I think I may have too many elements here because I'm going to change this thing, these two linear. You can see that the behavior of my CATIA is erratic here. So, okay. So let me go here, make sure that it is actually linear, so that I can rotate stuff, I can move things. This is where on the test, unless you're specifically asked, try not to use, do not use parabolic element. Okay, good, very good. Let's save our analysis file. So file, save management, analysis, save as in that same folder, which we call the tensile assembly. There's the product there and the parts there too. So we save it right there. Okay, what do we know? Now, these things are here, by the way. These are in hiding. They're still here. Okay. So these ends are clamped. So we have clamp at this end and that end. Very good. And these ends are being pulled up. Okay, if that they're being pulled up, so I'm going to say, okay, let me do it like that. Pulled up. I have to make it 0 first, right? I have to make it 0 first, correct? Pulled up, 0 first, and then I can change it. However, actually this face I want, not the edge. That face, based on the problem statement, is that face and this face. Now, I'm going to caution you, and this is, by the way, global. Global, right? Global. I don't have a local system here. What will happen, you will see that it's going to come back. This is going to bomb out because this can move to the left and to the right. When we use planes of symmetry, this is not going to happen, but here it will. So let's just leave it the way it is, and we're going to fix it. Okay, we're going to fix these one by one gradually. Now, now that I specified my low or restrain, now I can go and change this, right? I go and change this. So we go here to enforce displacement. You remember that? You click on this, and it says how much? 0.01 positive, right? 0.01, 100th of an inch upward. It looks like everything is done, except that you will see that it will bomb out several times until we take care of everything. All right. First of all, what's going to happen? It bombed out. So let's look at the deformation and let's animate it. You see this? Here, let's play it again. You see that? Because this can move as a rigid body. So let's stop this thing by not allowing it to move, for example, in direction Y and direction X, okay? Because after all we want to do is to take this thing and pull it up, okay? So double click on this and say, okay, in all three directions, and say, okay, and now run it. It will still bomb out. You'll see why in a minute. So let's look at deformation. Now you can see that that pin is not going to move in and out or does not rotate, but the block has no idea that there are two pins inside of these two holes. Whenever you do assembly constraints, whenever you do assemblies, you have to say how the parts interact with each other. So let me deactivate this. We know what the issue is. I told you that we're going to take these pins and insert it into that hole. The pin cannot penetrate this block up or down or sideways. Anyway, in order to do that, you have to create an analysis connection and call that thing to be contact. Okay, so here's the way you do analysis connection. First component, the surface of this. Second component, hide that and the surface of the hole. And then another one for down here, another analysis connection, surface of this. For the second component, hide that and the surface of the hole. By the way, the order doesn't matter. You take the hole first or the surface of the pin first, or the order doesn't matter. Now that we define these connections, we now have to say how they're connected. And that is where this face-to-face, face-face connection property comes into the picture. This is where it's coming to the picture. If you look at these, we're going to do most of these anyways, but right now, for this today, these are contact. Contact, you click on the contact, You select connection 1, analysis connection 1, right there. This is the icon for contact. You do it again, another contact for the second one. Notice that it's at the bottom here. And don't worry about these things because these are not checked. If these are checked, then you have to worry about these numbers, okay? But they're not checked for us. In this course, we don't do friction, we don't do stuff like that. Okay, so we define analysis connected, general analysis connection for the top two components, for the bottom two components, and then we declared, once we created these analysis connections, then we declared them to be contact, okay? Let's save everything first, and then run it. You'll see that it still bumps out. We'll see how. So run it. Okay, and if you say why this time? Can the pin actually go through this block again? The answer is no. Look at the mode of deformation. You click on it and you animate it. You see, it's the block that can slide inside of that hole as a rigid body. Okay, so I'm going to stop this. In fact, if you want to exaggerate it, okay, let's do it like that. Let's here, let me animate it now. You can see it's the block that's going back and forth. So we stop this thing, and now we're going to say, okay, deactivate this plot and prevent that rigid body motion. By the way, these pins are still here. Even if they're not showing, they're still here. It was just in hiding. Here, they're still here. You can see that. So I'm going to take one corner point and say, you cannot move in the direction Y. So user defined a straight. This corner point cannot move in the direction Y. That will take away the rigid body motion. Okay, and let's run it. And lo and behold, this time it will be fine. I'm sure it will be fine. Good. Look at the deformation. If you want, reset the scale so that you can see some motion right there and animate it. And this is exactly the way it should behave. So these ends are fixed. These two ends are pulled up. Okay. And this is the way it should look like. Now, you can look at the displacements. Average ISO. Change the rendering. Anything that's hurting your eyes, delete it, or not delete it, deactivate it. For example, restrain, right click, hide. Some of them are gone. These things you can hide. Actually, I think you can hide this whole thing. Good. These for loads you can hide. The load was actually this thing that's going up and down, right? Hide. And these connections, analysis connections up here, you can hide. That here. And properties, actually, these are properties I'm hiding. Good. Now, if you want to see the elements, go to the last icon with the question mark in the rendering. The elements will pop up. Actually, there is more than just the regular element. These contact elements are also showing up here. If you don't want to see that, say select. Just show me the block, the pin, top pin, and the bottom pin. Notice that you can see that actually a gap develops. It should, right? A gap should develop here if everything is correct, and there should be a gap down here also. Right there, you can see that. Right there. Okay, good sign. All right, now, how much force is needed to pull this up? It's the same thing that you did before. In other words, you go to sensor, right click, create sensor, create resultant sensor, reaction sensor, and it says where. Remember, you pull this thing up. Remember, actually pulling up was right here. Yeah, it was this one, right? And then say update results. So pretty much it's this number, right? It's this number. This is very small, right? This is very small. You can see that 10 to the minus 1. But this is about 2,000 pounds. Remember, this is a piece of steel 1-inch thick. Takes a lot of load. So when I do symmetry and reduce this, I'm not going to get that number. This is the correct number. But then when I do use symmetry, I have to multiply by something in order to get this number. This was almost 2,200 pounds. Okay. So that takes care of doing the problem without any planes of symmetry. All right. Now, to do the problem with the plane of symmetry, the two planes of symmetry, I'm going to close this analysis file, okay? Because I want to do another analysis file for you so that it becomes a review. However, I do have to go to my assembly and start cutting. So here's the split. Notice that we are in assembly design right there. See the two gears? You click on the split and read the bottom left corner of the screen. Select a plane, face, or surface, or an existing split. Now, so what it means is that what do you want to split it with? Well, one of them is this plane, cutting it along with the exit plane. It says when you do that, there are 3 parts that are going to be affected. Are you sure you want all of them? The answer is, or which one of them do you want? So I can do this, and I can do I select all of them, and it doesn't matter which side I pick, and I do another split. This time with YZ plane, and it says when you do that, these are the parts that are going to be affected. So obviously, if I want one of them not to be affected, I don't do that. For example, look, block I want it to be affected for sure. Let me go back here. Maybe the easiest way to do it is undo. Just undo. Okay, let's do it again. Oops, undo. Let's go back where we were, because you may wonder what happened. Okay, there we are. Okay, let's try it again. So split with this plane. Now, if you want all of them, you just do this. If you want, for example, with the control, I can do this and that. If you don't want anything, don't select it. But I want all of them. Instead of using control and doing this, I could have actually selected this. It would have done all. Good. So there we are. Okay. Now, if you want, you can also go at the part level and do this. It's up to you. But I did it at the assembly level. So this is an efficient way of basically in an assembly cutting several things at the same time. It's up to you how you want to do that. This is what you want. Okay. Now, I'm not going to do any saving here. So we're going to go to generative structure analysis. So the analysis is done fresh from the beginning. Notice that again, it kind of automatically measures these 3, measures the pins, measures the block, and I say okay, except that I told you that this, I want to do local measure around the pin. So let me change the rendering here so that we can see better. I'm going to double, let me hide this, hide that, hide this, and hide this bottom one. Okay, so now we're going to say, local mesh size. It says, well, it doesn't do anything because it's expecting you to say, what do you want to refine? Well, obviously, I want to refine the block. Double click on this, and then it says where. Okay, I want it here, refined here, and I want it refined there. Okay, 2 surfaces, and this is the size. Here's the size. You can see that right there. Good. And now if you say, show me the mesh, it'll show you that the block has been refined in that area. You can see that. You see this? The block is refined here. For the pin, it was already small anyway, so the block is refined here. Okay, very good. Deactivate this. Now, what was the next step? The next step was the order doesn't matter. You can create a connection, analysis connection now, or you can do it later. That's entirely up to you. If you want to follow the way I did it earlier, so okay, so let me do that. That may not be a bad idea. So let's bring this thing in the front. This thing in the front. Let's go back there. So what did we do? We first clamp this end. Okay. Now we have surface slider. These are planes of symmetry that are created. So there is this half a circle. There is this other half a circle. And there is that piece, rectangular piece, whatever is left of it here. And now turn around. You can do it all at the same time. It's this block, this pin, half of the pin. It's that top piece. This is from the block. This is from the block. Go down here. That is from the block, and this is from the block. Any one of these missing, unfortunately, you're going to lose the mark for that particular part of the problem. Okay, good. Now, then I'm going to say, okay, I want to pull this thing up, remember? So we're going to say this piece in the vertical direction, which is Z, 0. Now, remember this pin was going in and out? It cannot go in and out. However, it can still spin. I will leave it like this to show you that we may have to come back. Actually, it can't spin because of this. So that's okay. It will not come in and out, and it will not spin. So this should be good. This should be good. Okay, very good. And now enforce displacement. You can do it from the tree. It's these little arrows here, red arrows, or you can do it from the tree. I think it's this, right? Yeah, it's this. And 0.01, exactly what it is. Okay, so we run it. Hopefully everything is going to go through. I think it should be fine. Oh, maybe the spinning will be an issue. Let's find out what happened here. Let's see. Oh, no, it's not the spinning. I forgot to create connections. It goes through it like butter. Okay, so let me deactivate. Completely forgot about connection. Remember, I said that whenever you assembly, you have to describe how the parts interact with each other. Okay, so here's analysis connection. Click on it. First component, surface of the pin. The order doesn't matter. Second component, the surface of the hole, right there. Again, the order doesn't matter. And this is the one that we just created. It's right here. You can do them one by one, or you can do it here and say what it is. It is contact, right? Face-face connection, right there. Face-face connection. Here is contact. But so that I do it exactly like I did it the earlier version without any planes of symmetry, let's do that the same way. Analysis connection. First component is the surface of the hole. Second component. Actually, I picked the pin first, doesn't matter. Second component, surface of the hole, right there. So these are the analysis connection, and you want to declare them to be contact. So look at the face-face connection. This is how you create it. You say these guys are related to each other. Maybe they're siblings, maybe they're friends, maybe they're classmates, okay? So this doesn't say how they're related. These say how they're related. Okay, so this is contact connection. For the first one, you have to do that separately. And then another one for the second one, you cannot simultaneously pick them. See that? Contact. And now run it. I bet this time will work. This is just a rotation. Let's see. Let's change the scale here so that we can see what happened. Right there, you can see. Anything you don't like, you can hide. So connections we can hide, elements we can hide, properties we can hide, restraint hide, load hide, and these guys hide. So it's nice and clean. Maybe I have to do this. Hide, hide, and hide. It's nice and clean now. Hide. Very good. Displacement. If you want to see them, just show me the block element, the pin element, top one, and the bottom one. Don't show me all those intermediate contact elements. I don't want to see it. And average ISO. Change the rendering. There we are. And if you want to see your element edges on the rendering, go to the last one. Because this box is checked, it just shows you the element width. Now you can see that the gap has developed here. And the gap has developed here, as you expect. You can see that right there. You can see this. Okay, and stress distribution. The stress distribution, if you want to see von Mises stress distribution. Now, notice that actually, because why don't we just look at the block? Okay, stress distribution due to the block. So double click on this, and on the selection, just say show me the block. There we are. So that we don't get to see the stuff for the pins. Now notice that the pin goes up. That's why there's a big stress here. Okay, and let's see now down here, the pin, this piece is pushing or pulling up on this fixed pin, and that's why there's some stresses there. If you want to see where the biggest stress is by any chance, and if you trust these, of course, you click on this in this toolbar, analysis tools, where you have a strip of film, and you can click on this one that says M&M, maximum minimum, and just say OK. It shows you the maximum location is right up there. You can see that the maximum stress is right up there. Okay. This is without the pins being present. Now, with the pins being present, the maximum location may be some other place, okay? I suspect it will be the same location, but it doesn't have to be in general the case. Now, let's look at, by the way, you know what? Why don't we also look at this was linear. Remember, it was linear analysis? Let's do a parabolic one and see what happens. This obviously will take longer, but let's see. A little bit longer, not by much. Probably because this is not a big model. Later on, we're going to check the force. The force needed to pull this thing up, and we'll see that it's not that number that we got before. It's a portion of that. So let's activate this first of all. Yeah, actually, you can see there's significant change. There's about maybe 15% change from previous one. So nothing can be trusted right now. But let's look at the load. So if you look at the load, you put the cursor there, right click, create resultant sensor, reaction sensor, and let me remind you, you can either go to where you pull this thing up or you can go to the clamp. That's entirely up to you. So pulling it up right there, update. This is going to be 3000. So the load that I actually need to do this is going to be 4 times that. 4 times that. Because remember, this sample that we have has the other side and mirror like that. So basically we have taken 1/4 of that. Now, I don't trust any of these numbers, but if you want there, this may be a big deviation. Why don't we go and run it with linear? Because that number that we had there was for linear one, it wasn't for parabolic. So let's go back here and do it with linear. And by the way, the mesh there was different too, as far as the size and things like that concerned. But anyway, let's see. Okay, let's run it. And now look at the, once we get it, let's look at our uh, force. Okay, so let's go here. You already have created the reaction force here. That's good because I need to see this thing when I'm marking your papers. Double click on that. It didn't change that much. Okay, it didn't change that much. Okay. I think, let me see for a second. Here we have to take this and we have to multiply it by 4. And that should be the same as what we got without any planes of symmetry. Now, I can't remember what we got without any plane of symmetry, but remember, I don't have any confidence in any of these numbers because we haven't done mesh conversion study. But if you believe this is true, you have to multiply this thing by 4. Yeah, you have to multiply this thing by 4 in order to get the actual load. Okay, because this is the load for this 1/4 of the sample that we have modeled. All right, folks. So please make sure that this is right there. And if this was a test problem, I asked you, provided you with a place where you have to write down how much force is needed, write down 4 times this number. Okay? Good luck.